Hi everybody, welcome back to the Feynman Technique. Today we're going to be taking a look at this integral that I miswrote originally. It's actually sine of natural log x times natural log x over x plus 1 all squared. Alright, we'll be using this fact that I derived in a previous video. I will link to that video in the description. So let's get started. First step is, I'm not going to show the work involved in this. But we can jump right to I being equal to 2 times the integral from 0 to 1 of the sine of natural log x times natural log x over x plus 1 squared dx. That comes from breaking this up into 2 separate integrals and then performing a substitution on the second one. If you've watched my other videos, you probably saw that right away. You probably knew that I was going to do this. All right. So the next thing we want to do is rewrite our sine natural log x. So let's remember that e to the I something is equal to cosine something plus I sine of something. In this case, our something is going to be natural log x. Now, using the properties of logarithms, we can make this e to the natural log of x to the I. The e and the natural log cancel out, giving us just x to the I. Now, if we take the imaginary part of this, we will just be left with sine of natural log x. So, in other words, the imaginary part of x to the I is equal to sine of the natural log of x. All right, so let's use that. Actually, I'll rewrite that. So the imaginary part of x to the I is equal to sine natural log x. So we're going to rewrite our integral now as I is equal to 2 times the imaginary part of the integral from 0 to 1 of x to the I times natural log x over x plus 1 squared dx. Okay. All right, so now what I want to do is I'm actually going to label this expression right here f of t, because it is a function of t. So let's just say that f of t is equal to that thing right there. Okay. Well, if f of t is equal to that, then let's take f prime of t. Let's see. Well, our f prime of t as an integral would be the integral from 0 to 1. Sorry, that's f prime of t is equal to the integral from 0 to 1 of x to the t natural log x over x plus 1 all squared dx. So from there, we can get this. If we take the imaginary part of our f prime evaluated at the point I, 2 times the imaginary part of our f prime evaluated at I, we will recover our original integral, right? Because if we plug in I for this, we get the integral from 0 to 1 of x to the I natural log x over x plus 1 all squared, which is this thing right here. And then multiplying it by 2 and taking its imaginary part gives us I. All right. Well, that doesn't help us as is, but we know that we got this by taking the derivative of this. So we can also get f prime of t by taking the derivative with respect to t of this thing. So let's do that. So if f prime of t is equal to this, then f prime of t is also equal to the derivative with respect to t of this sum. So that's going to be equal to, well, actually, we aren't going to need the parentheses anymore because this 1/2 will drop out when taking the derivative. So that's going to be the sum from n equals 1 to infinity of the derivative of t over n plus t with respect to t. Well, what would that be? We get, let's see, low d high minus high d low over n plus t all squared. And of course, all of this would be times -1 to the n. Let's see, our low is n plus t. D high would be 1 minus high, which would be t, and then d low with respect to t is just 1. So we would, on the numerator, we'd have n plus t minus t, or simply n. So let's just write it like this. -1 to the n times n over n plus t all squared. That will be our f prime of t. Okay, so now let's take the imaginary part of this. Oh, I'm sorry. Let's evaluate it at the point I. Take the imaginary part and multiply it by 2. And that will give us our final answer. So let's see. That's going to give us I being equal to 2 times the imaginary part of the sum as n equals 1 to infinity of -1 to the n times n over n plus I all squared. All right, so how are we going to take the imaginary part of that? Well, we can't really do that easily when we have an imaginary number in the denominator, but we'll use the standard method of multiplying the top and the bottom by the complex conjugate of this, but we'd actually have to multiply it by this thing, the complex conjugate of this all squared. All right, so let's see. If we did that, we would get n minus I all squared times n minus I all squared. All right, so let's rewrite this. That means that I is going to be equal to 2 times the imaginary part of the sum as n goes from 1 to infinity of, let's see, that's going to give us n squared, sorry, that's an I, n squared minus I squared, or in other words, n squared plus 1 all squared. That will be our denominator. N squared plus 1 all squared, right? N squared plus n I minus ni minus I squared, but that would just be plus 1, and then all that's squared. So yeah, that's right. And then we'd have, well, let's see, we'll still have this -1 to the n. And what's n minus I squared? Well, bring up that n, and then we'll have n squared minus 2in, and then plus I squared, or minus 1. Okay. So now all that's left to do is take the imaginary part of this, and we are done. So that means that I, our original integral, is going to be equal to 2 times the sum as n goes from 1 to infinity of -1 to the n times, let's see, the only thing that's going to matter in this is the -2in. So that's just going to give us, let's see, taking the imaginary part of that would give us -2n squared. Right? Bring in that n inside, we get -2n squared. That's right. Over n squared plus 1 all squared. And then we can go ahead and take this 2 out, I suppose, and make this 4 times the sum from n equals 1 to infinity of -1 to the n. And then we'll go ahead and bring this negative sign out as well. Get rid of these parentheses just to clean it up a little bit. And that is the final answer. And you could probably go a little bit further with this. There might even be some special function representations, or you might be able to go further with this. But in my opinion, like I've said before, having it expressed as a sum like this is good enough. If you had the time, you could come up with an answer that is very close to the true answer to that integral right there. So there you go. Hope you enjoyed that.